Hello everyone, this is Neha Sisodia, Assistant Professor at New LJ Institute of Engineering and Technology. We are going to discuss query processing and optimization. Query processing and optimization are part of our 5th unit, and we are going to discuss query equivalence today. Now, as we have seen in the previous discussion that the relational algebraic expression can have some intermediate form that can be evaluated by an optimizer and ultimately can be executed. So transformation of the relational expression and finding its equivalent that will produces the same result as the original query do, that is called as equivalent query. So two relational algebra expressions are said to be equivalents if every legal database instance of two expressions generate the same set of tuples. So what we have to note here is the order of the tuple is irrelevant. So in any order if we take it, we will generate the same number of tuples and the same set of tuples. So in SQL what happens is the input and output are multi-sets of tuples. So two expressions in the multi-set version of some relational algebra are said to be equivalent if on every legal database instance, two expressions generate the same multi-set of tuples. So an equivalent rule says that the expression of two form are equivalent and can replace the expression of the first form by the second and vice versa. So in place of the original query, that we can use the equivalent expression of it. So there are certain rules for equivalence. What we can do is, if we have to select something from the conjunction of two conditions, we can have the selection of sequence of individual operations. Similarly, second number rule says that the selection operations are commutative as well. Like if we have selected one in the inner one and the second one at the outer one, we can exchange their position. So only the last in the sequence of the projection operations are needed. The other can be omitted. That says the rule number 3rd. That means the last one for the projection has to be the last answer. So the selection can be combined with Cartesian product and theta join. That represents rule number 4. So for example, we have to select some theta from an expression E1 and E2, the Cartesian product of E1 and E2, we can replace it with a join and the condition theta. Similarly, if we have the subsequent theta joins, we can use it with conjunction of both the theta conditions. Now in theta operations and natural joins, they are also commutative. We can exchange the position of the relationship if we have taken it in some order. Rule number 6 says the natural join operations are also associative. Secondly, the theta join are associative in following manner, like if we have expression E1, theta 1 join expression E2, and we have conjunction of two theta values, theta 2 and theta 3 with E3, we can exchange these values one after another. So theta 2 involves the attributes from E2 and E3. So this is the pictorial depiction of equivalence rules. If we have E1 and E2, the rule number 4 says we can replace the position of E1 and E2. Similarly, E5 says that we can evaluate the join over E1 and E2 or E2 and E3 first and then to E1 or then to E3 are equivalents. Similarly, rule number 6a says if theta only has an attribute of E1, what we can do is we can replace the selection and join theta condition before and after. Rule number 7 says the selection operation distributes over the theta join operation under two following conditions. The first one says when all the attributes of theta 0 involves only the attributes of one of the expressions E1 being joined, that is theta 0 and E1 expression and theta and E2, we can replace it by E1 will have a selection of theta 0 and then we can join it over the condition theta with E2. Secondly, when theta 1 involves only the attributes of E1 and theta 2 involves only the attributes of E2, what we can do is we can put a conjunction that theta 1 and theta 2 with theta 1 joined with E1 joined with theta condition with E2. So what we can do is we can individually give a selection condition over E1 expression and E2 expression and then we can join it over theta. The eighth rule says that the projection operation distributes over theta join operation as follows. Like if we have a projection of L1 union L2 and we have a theta condition over both the expression, we can distribute it over L1 and L2 over individual expressions E1 and E2 and then we can join it over theta. So consider a join theta over E1 and E2. We have L1 and L2 be the set of attributes and E1 and E2 have the expressions respectively. So let L3 be the attribute of E1 that involves the join of condition theta, but they are not in L1 union L2. And let L4 be another attribute of E2 that is involved in join of condition, but it is also not the part of union of L1 and L2. So what we can do is the expression can be reevaluated as we can project it from the combination of L1 union L2, but we can have an individual projection of E1 that represents L1 union L3 and L2 union L4 from E1 and E2 respectively. We have few more rules over it. The ninth rule says that the set of operation union and intersection are also commutative, but set difference is not commutative. So the 10th rule says that the set union and intersection are also commutative and they are also associative. The rule number 11 says that selection operation distribute over union, intersection and also on set difference. As we can see in this example, we can distribute it over union, intersection and set difference. The projection operation distribute over union. Now, suppose we want to transform a query. Suppose I have to find the name of all the customers who have an account at same branch located in Brooklyn. So I will select customer name and we have to also filter out the branch city with Brooklyn and we have to find it out whether they are customers, they have the account holders and they are also depositors. So along with the branch, account and depositors, we have to filter it out with the city and its customer's name. So what we can do here as a transformation rule, as 7a we have seen, we can distribute it over, we can select individually the city of Brooklyn and then we can go with the join of account and depositor. Then we can find ultimately the name of the customers. That will filter out only the tuples from the branch which are associated with Brooklyn. So performing the selection as early as possible actually reduces the size of relation that has to be joined. We also have some multiple transformation examples. So for example, we need to find the name of all the customers we are having account at Brooklyn branch and whose account is having a balance over $1,000. So what we can do is, as in the previous query, we just have to put one more constraint like in the branch city, that will be Brooklyn only, but we also have to get the balance which is greater than 1,000. So what we can transform in the second query is, we can take the individual values here as a Brooklyn and also we can have the balance which is greater than 1,000. So we can transform it and we'll keep the selection as early as possible to reduce the relation which will undergo join. So this is how the initial expression tree that we have evaluated as branch, account and depositor for branch city in the Brooklyn and the balance greater than 1000, less than 1000 and customer name. So the tree after multiple transformation is going to be changed as we will get a selection over the city, we will get a selection over the balance, and we will have the depositor at the last, so that we'll get the customer name which are filtered by these conditions earlier. Now we have projection operation as an example. Suppose we need to get the name of the customer who is from branch city Brooklyn, and we have to compute the relation like the individual value of the city which is in Brooklyn from branch, and we have to join it to the account. So we obtain the relation whose schema is branch name, branch city, assets, account number and balance, which are the attributes of account, and branch name and branch city are the attributes of branch. So push projection using equivalence rule 8a and 8b, we will eliminate unneeded attributes that are not required in the intermediate results. So what we can do is we will get filtered the branch city as Brooklyn, and we will join this to the account, and after that we will from the filtered values we will get the account number from the tuple of the joined relationship branch and account, and after that we are going to join it to the distributor in order to get customer name. Now join ordering example we'll have is for the relationship if we have R1, R2 and R3 are three relations where we have R1 and R2 are joined together, and then we have R3. So we can associate it. So this is also associative. If R1 and R2 are joined, the R2 and R3 are joined and they are quite large. So what we can do is R1 and R2 are small. So we can individually join it with the smaller relation first, and then we can compute it afterwards with a larger relationship. So we have certain example for this, as we have seen in the previous one as well. If we want to consider the customer name with the branch city Brooklyn, so what we can do is we can individually do it as an associative rule as we have seen earlier. Now enumeration of equivalent expression, what says that the query optimizer use equivalence rule to systematically generate the expressions that are equivalent to the given expression or the original expression which has been given. So conceptually what it do is it generates an all equivalent expression by the relations and repeatedly execute it following step until no more expressions are found. So for each expression found so far, we use all the applicable equivalence rules and will add newly generated expressions to the set of expressions found so far. So the above approach is very expensive in space and time, and it's difficult to evaluate, and the complexity will also rise. So the space requirement reduces by sharing some common sub-expressions if we have in our expression. So even is generated from E2 by an equivalence rule. Usually only the top level of the two are different and the subtree below are same as that can be shared. So time requirements can be reduced not by generating all expressions. We need not to generate all the intermediate expressions. We can reduce the time complexity. So this is what is the evaluation plan, and evaluation plan actually defines exactly what algorithm has to be used in order to execute the query, and will also reduce the time and the space complexity of the execution. So what we can do is we can use some pipeline in order to execute the query. We will see pipeline exhaustively in our upcoming sessions. So what will be the choice of evaluation plan? we must consider an interaction of evaluation techniques which we are choosing for evaluation plans. So choosing the cheapest algorithm for each of the operation independently sometimes may not yield the best overall algorithm. For an example, suppose we have a merge join, it may be costlier than a hash join, but provided the stored output which reduces the cost for an outer level aggregation. Sometimes it happens that nested loop may provide opportunity for pipelining. So the practical query optimizers actually incorporated some elements of the broad approaches that are listed, that is searching all the plans and choosing the best plan in the cost based fashion as we have discussed previously, and it also uses some heuristic plan to choose the best out of it. We are going to see some joint strategies in query processing and effective evaluation of query in our next subsequent video. Thanks for watching this video.